Welcome back, dear students. Today we will discuss of next example for coordination compound, in which we will try to consider shape, geometry of a molecule and its magnetic property. Let us consider the next example, that is NiCN4 2 minus. Generally such questions can be asked for your board examination for 3 marks and for the competitive examination around 4 marks. So when you consider NiCnO4, we must first and foremost need to know regarding the oxidation state for the central metal atom or the transition metal which is present here. And after that, soon after that, we are supposed to check out whether ligand which is approaching to the central metal atom is a weak field ligand or it is a strong field ligand that we need to identify. As I told you, ammonia, CN, all having like ammonia, CN, generally they will be coming as a strong field ligands, and halogens, I told you, they will be considered as weak field ligands. In this case, I have CN. This is said to be a strong field ligand. Cyanide group is strong field ligand. Strong field ligand. Okay. Once the strong field ligands approaches to the transition metal, the electrons are going to be paired up in the d orbitals. Electrons are going to be paired up. If weak field ligand is approaching, electrons do not pair up. That is the main difference we need to know with respect to these ligands. So as per the CN, that is cyanide ligand, which is strong field ligand, pairing of electrons takes place. Pairing of electrons takes place. Once pairing of electrons taking place here, the whole complex, coordination complex, of which we are trying to writing shape, geometry and properties of, will be considered as diamagnetic. It will become diamagnetic. Diamagnetic. So this is nothing but a magnetic property. Okay, so this is all about the ligands approachment. Now as I have nickel present over here, okay, so nickel's electronic configuration, if you consider 3d8 4s2, it will become. We supposed to remember the electronic configuration for almost a 3D series. Maximum of the transition metals will be taken for making the coordination complexes from the 3D series itself. So that is the main criteria we need to remember. So 3D series, we all know it's transforms scandium, titanium, iron, zinc. As we are considering nickel here, we know that chromium and copper will be exceptions because they are considered as half filled and completely filled. That is the main reason they are exceptions while writing the electronic configuration. And from scandium, it is 21, 22, 23, 24, 25, 26, 27, it is 28, 29, and it is zinc is 30. So when you have 28 here, we need to consider argon configuration. Okay. So argon, and we have nickel as 28. Now it is becoming 3d8 4s2. 3d8 4s2. Okay. So 18 plus 10, 2, 20 plus 8, 28. That is electronic configuration for nickel. Now once we write electronic configuration for transition metal, next part we need to understand what is the oxidation state of the transition metal present in the coordination complex. Let us check that one. I have nickel here. Let me consider this nickel as X. Okay. And Cn will be donating 1, that is negative ligand it is. We will be having -1 charge on it. How many of them are there? There are 4 are there. So total charge they have given as -2. X minus 4 equal to -2. Then X will become 2. So like this we need to do the calculation. So in the sense, nickel is present in +2 oxidation state in this coordination complex. If it is present in +2 oxidation state, we need to consider 3d8 itself. Argon 3d8 configuration we need to consider. That means only 8 electrons supposed to be arranged in the d orbital. So this is all about the very basic thing. It is not necessary that we all have to write each and every part for 3 marks. No. It is just that for your knowledge purpose, I have told you how to write the electronic configuration first, and then we need to check out the oxidation state. If at all directly you will be able to predict the oxidation state of the transition metal, it is well and good. Yes, that's awesome from your side. It is not necessary that you are supposed to write everything. Okay, so like this we need to do. Once we complete writing the oxidation state, now next we are supposed to consider electrons are going to be written in a d orbital. Let us do that one. So I need to represent 8 electrons. I will rub this one, and this, with the help of this explanation, you can come to know the whole complex is said to be diamagnetic. Okay. Now let us see. We have 3d8 4s2. Ni plus 2 only we supposed to fill 8 electrons. And remember, pairing of the electrons is going to take place. So let us consider 3d orbital. Okay. 1, 2, 3, 4, 5. Once we have 3d, we will be having 4s. 3d, it is 4s, and we also have p orbital present, 4p. Now let us fill the electrons. 8 electrons we supposed to fill. 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons are filled. Now check out how many ligands are approaching to the transition metal. There are 4 ligands are approaching. 4 CN groups are approaching. When the 4 CN groups are approaching, each will provide 2 electrons. We need to make them place to accommodate the orbital. As the ligand is a strong field, electrons will pair up here. So how does pairing takes place? Only the one electron, it will get paired here. So next, how you would see this one? It will be done with the pairing. 1, 2, 3, 4, 5, 6, 7, 8. It is empty now. Then I have 4s with me. Then I have 4p also. Let us give 4 places for 4 ligands approaching to the transition metal. Approaching to the transition metal. So CN1, CN2, CN3. Every time it is not necessary that you need to mention this is CN. Directly if you arrange the electrons with respect to geometry as well as hybridization, that is more than enough for 3 marks. For your knowledge, in order to make the things still clear to understand you, I am writing each and every point. So here, as I empty d orbital, this d orbital 1, 2, 3, 4. 2 of the p orbitals are going to be involved in hybridization. So after hybridization, what happens? You can see here 2 electrons. This will be giving here, this will give here, and this will be giving here, right? Okay. And one more ligand is going to be involved here, that I must mention this side. So this ligand gives here, this will be given to this orbital, okay, and this will be giving here, and finally this is going to be given here. 4 ligands, we need to make 4 orbitals free to accommodate a ligand. So once you've done this one, can you see this structure? How does it looks like? What will be the hybridization you will find now? This is d orbital, okay, this is s orbital. There are p2 orbitals are there, px and py. p2 orbitals will be occupied. Now you can see here, what will be the hybridization I must write? Let me first fill this one. Total electrons, this is d, this is s, these are p, right? Out of 3p, we need only 2p here. dsp2 hybridization it will form. Okay, so 1, 2, 3, 4. Only 4 we need here. So 1, 2, 3, 4, 5, 6, 7, 8. 4 ligands are approached here, and the hybridization I would write here, it is DsP2. It is DsP2. Like this, we have to find the hybridization part. So once we have written here hybridization, we must have to think over whether inner d orbitals are involved in the hybridization or outer d orbitals are involved. That we have to check out. You can see here, we see very easily, this is 3d. After 3d itself, we will be having 4d. So here, arrangement of the electrons has taken place in the d orbital, that is inner d orbital. And the reason why this complex is said to be inner orbital complex. Conclusion, let us write here at the later. It is said to be inner d orbital. Fine. That is second point. Then next point we have to check out here with respect to this example, that is magnetic property. The magnetic property exhibited by this complex, as I already told you, strong ligand is approaching here. When strong ligands are approaches, rearrangement of electrons, that is shifting of electrons, pairing of electrons takes place, and the whole complex will become diamagnetic in nature. So once property is completed, that is inner orbital DsP2 hybridization, we have concluded it is inner orbital complex also. Now we need to understand the shape of a molecule. How does it exist? Let me write each and every point here. So once DsP2 hybridization is involved here, you can see nickel will be present at the center and 4 Cn will be arranged at the 4 corners of a transition metal like this. Okay, and whole we will be writing the charge over as -2. Getting? So like this we will be writing. What this type of the shape is called as, it is said to be square planar. Square planar. So this is all about the thing we have understood. So after just doing these parts, at the conclusion part, at the last, you supposed to write regarding the properties of this complex. I'll write here one by one. I'll rub it and I'll be writing here below. You can check out that one and write each and every point properly. And all the things what I explained here should be written in a point wise. It is only for the 3 marks. No need of writing each and every explanation. Point wise, if you write, that is more than enough. So what is the hybridization we have found for this one? Yes, it is DsP2. Okay. So what type of complex it is? Inner D or inner orbital complex. Second point. Third point, as strong field ligand is approaching here, is said to be diamagnetic complex. Diamagnetic complex. Lastly, what about the shape? Shape of a molecule is said to be square planar. Shape of a molecule is said to be square planar. How does it look like? Cn, Ni. There are 4 Cn are approaching. This is Cn, Cn, Cn. 2 minus. That's it. So if you complete this much by explaining each and every point, point wise you have to write, you will definitely get 3 marks for this question. Please do copy this. We'll move to the, some of the drawbacks are there. Yet all these things, only the thing is when we confirm that ligand which is approaching to the central metal atom is of whether it is strong field or it is weak field, then only we can predict the magnetic property. If at all we don't have any idea regarding these ligands, then we couldn't predict the complex magnetic property. And these transition metals which are present here show some kind of coloring property. You know, some of the complexes, they will be showing us a kind of brown color, yellowish color and so on. Why does that color is exhibited by these complexes was not explained by VBT. Coloring property as well as magnetic property of these complexes is not explained by the valence bond theory. The reason why we found those all are drawbacks. So we'll see what are the drawbacks of valence bond theory in order to overcome those drawbacks which was shown by VBT will be studied in detail with the next theory, crystal field theory. Please do copy this. We'll move to the drawbacks, then we'll move to the crystal field theory. As I have told you, dear students, there are certain limitations or drawbacks are present with that of the valence bond theory. When you consider the drawbacks, very first it is said that this whole valence bond theory is based on number of assumptions. We have to assume that the ligand is strong field or it is weak field. That also one of the assumption. We have to very first know regarding the magnetic property. Once we know the magnetic property, then only we can predict further. And there is no proper explanation for the coloring property. I give you very small hint for the coloring property. Why does coloring property is exhibited by these complexes? I just give you one hint. Whenever we consider a transition metal in a ground state, it will be very stable. Okay. Once we provide certain amount of energy to the ground state transition metal, certain amount of energy given is going to be absorbed by it, and the electrons which are present in that transition metal will be moving to the higher energy state. When they move to the higher energy state, they are not much stable as they before. In order to gain their stability back, they will be coming back from excited state to ground state. While coming back to the ground state, they will be releasing certain amount of energy which is absorbed while going to the excited state. That energy which is released while coming back to the ground state will be seen in the form of color. That energy which is liberated is seen in the form of color in the visible range. That is the main reason why these exhibit colors. That explanation was not dealt or was not clearly given by valence bond theory. That point, and it doesn't give us any kind of reason for the stability of the complex. Whether the complex is having square planar or different type of a shape and geometry, whether it is 100% stable in that case or no, that was also not explained by valence bond theory. Fine. Then magnetic property. As I already told you, magnetic property is completely dependent on the type of a ligand approaching. We must have to know regarding the ligand property, whether approaching ligand is a strong field or it is weak field. That must be known as well before. That explanation was also not given by valence bond theory. So the reason why all these are considered as limitations or drawbacks of valence bond theory. Once it is exhibiting such type of drawbacks, the next theory comes which explains regarding these drawbacks, and till today we will be following some of the improved theories for coordination compounds. So please do copy these drawbacks or limitations for the valence bond theory. They may ask you for 1 to 2 marks. So please do remember, very easy it is. First one is it is based on number of assumptions. Second one is it couldn't give a proper explanation for coloring property as well a magnetic property. Lastly, it doesn't explain regarding stability of the complex also. So these all are said to be limitations. Most important limitations I have tracked here and have written. Please do copy this. We'll move to the next. Welcome back, dear students. Let us start with next part, that is crystal field theory. In short, we call it as CFT. CFT stands for crystal field theory. Okay. Now, we supposed to have certain postulates or points regarding the crystal field theory. So, very first point I supposed to tell here that these ligands, that is ligands and metal ions which are present, previously it is been explained or understood that there is a coordinate bond exists. But according to crystal field theory, it has given explanation regarding the electrostatic force of attraction forms a electrovalent bond. Okay, electrovalent bond is also referred as ionic bond. It is giving explanation that ionic bond or the electrovalent bond is existed between central metal ion as well ligands. That is the first point. Next, see here, the metal ions are generally said to be cations. They will be having a positive charge. Like that, ligands are also present. Ligands are said to be charged. We know that there are three types of ligands are existed: positively charged, negatively charged, as well neutral ligands, right? So when you consider ligands, they are supposed to be called as anions, and there are certain neutral ligands are also there. They are explained based on dipole nature, and the neutral ligands are said to be CO, NH3, H2O. Such ligands are going to be explained with the term dipole, right? Next, if there is no ligand present, I explain this thing very well to you in order to understand the complete concept of the coordination complex, but the thing is, do concentrate towards me. If I start with the explanation regarding this one, that is next point, third point. If there is no any ligand approaching to the transition metal, in the sense transition metal alone is present, near to that, so or up to the far away, no any ligand is approaching, then it will be having 5d orbitals present with transition metal. I repeat my words. If in the absence of ligands, no ligands are present, no ligands, then the transition metal will be present with 5d orbitals, and the surprise is that all the 5d orbitals which is present surrounding to the transition metal, all are degenerate. What do you mean by degenerate now? Degenerate in the sense all of them which are present are having same type of energy. Degeneracy is nothing but same type of energy. I repeat my words here. Just see, whenever we don't have any ligands approaching to the central metal atom, then transition metal will have 5 degenerate orbitals with it. What are those degenerate orbitals it has? They are said to be dxy, okay, dyz, okay, then dxz, dx square, y square, lastly dz square. So these are the orbitals present with the transition metal, and the thing is, all are having same set of energy. As they have same set of energy, the reason why they are called as degenerate orbitals. Now you can see how to represent that one. dxy is exactly equal to dyz, dyz exactly equal to dzz, and so on. So these are said to be degenerate orbitals in absence of ligands. In the absence of ligands. Fine. So now next you can see here. If the ligands approach to the central metal atom, this degeneracy is going to be lifted. Degeneracy is going to be lifted. What do you mean by degeneracy is lifted? So I will show you in detail. I have 5 pens here. Okay, these are 5 pens I have with me. Now I am keeping these in my palm. Okay, if these are said to be 5d orbitals of transition metal, okay, in the absence of ligands. Now you imagine, in some of the ligands are approaching from this side. As soon as the ligands are approaching here, the degeneracy is going to be lifted. Means some of the orbitals will come up and some of the orbitals remains as the same same place. Some of the ligands will come up and some of them will be remains as it is. This is nothing but lifting of degeneracy. Some of the orbitals will get higher energy, they will lift up. Some of the orbitals will be remaining as it is. Getting my point? That is nothing but lifting of degeneracy. Okay, so this is all about this one. See, for example, I have here 5 orbitals present of transition metal. As soon as ligands are approaching here, some of them will be lifted above and some of them will be remained as it is with respect to these lifted orbitals. Okay, with this we will learn in detail when we move to the further. And one more thing, VPT has given complete explanation along with the octahedral and tetrahedral complexes. VBT has given explanation same for octahedral and tetrahedral complexes. But in crystal field theory, the crystal field theory explains regarding octahedral complexes as well as tetrahedral complexes separately. It has given us clear picture regarding the octahedral complexes and tetrahedral complexes. Both are different. Both will be having separate explanation with the help of crystal field theory. So these all are the points or the postulates we can call for the crystal field theory, and we can understand what will happen with tetrahedral complexes and what will be the condition for this octahedral, tetrahedral differently. We will start that one. Please do copy this. We will finish it and we will start with the complexes. Okay, dear students, now let us start with the next explanation for the CFT. As I told you, there are 5 orbitals, d orbitals with a degeneracy, with the same energy they will be existed. Okay, so these are the d orbitals which are present in particularly transition metal. So dxy, dyz, dxz, dx square, y square and dz square are the orbitals. You can see here, in case of dx square and y square, orbitals are present along the axis. As well in dz square, there are orbitals present along the axis. Do remember this point. And rest of them all show orbitals are present in between the axis. Okay, so now all these together, what I have written here in a separately, they will be present together in a single picture or single representation. We'll see how to do that single representation. All these things are not at all necessary in writing the exam, but the thing is, in order to understand the concept clearly, so that to write the exact points in the examination, I'm giving all those things. There is no necessary to draw all these diagrams and all. I would have told you directly by taking the examples. Nothing will go in your hand, it will go out of your mind. In order to make the things still clear, I am drawing all these things separately. See, how does a single representation of all these orbitals can be done? We'll see. Single representation of all d orbitals. We'll see here. Okay. Now, see. Let me show all those things here. I have dxy. I have dyz also. X, y, z. Okay. So this is the thing. Now let me represent first orbital in this structure. Let me show with the black only. Here, these orbitals are present in between x and y. In between x and y. So how to show that one? See. Like this. What about other in between y and z? In between y and z. That can be shown. Like this. Okay. So just imagine x, y, that is dxy, dyz as well as dxz also I will show here in this only. Xz in the sense in between x and z. Okay, I must represent here one more orbital. It will be somehow like this. It is not necessary that you have to draw it. It is just for imagination that orbitals will be existed in this form in a metal ion or metal central metal atom. Now we supposed to represent x square, y square as well as z square. Can you see here? X square, y square are present along the axis. They are present along the axis, right? As well, dz square. Dz square is also present along the axis. Right? Like this, you can see the complex structure after combining all of these in a one representation. Ligands will be present in this fashion. Now we'll see how does degeneracy is going to be lifted when ligands are approaching. This is the case XYZ. What I have taken is, let us perform with respect to octahedral complex. We all know when we consider octahedral complexes, ligands will be approaching from 6 sides. That is, see here, this is the first ligand approaching, second ligand approaching, okay, third, fourth, fifth, and it is said to be sixth ligand. Let me show ligands in this fashion. Okay. So these are said to be ligands approaching to the central metal atom. When the ligands are approaching to the central metal atom along the axis as well in between the axis, what will happen? We will be having certain ligands which are approaching along the axis. We have certain orbitals present here. What are those orbitals present on the present along the axis? They are said to be dx square, y square, and dz square. When the ligands are approaching, just think that ligands are approaching along the axis. Along the axis. I repeat my word. When ligands are approaching along the axis, then what happens? Orbitals which are present along the axis are going to be repelled. By the orbitals. Ligands are going to be repelled by the orbitals which are present along the axis. See here. These will also have certain amount of energy which are present along the axis like this. And ligands approaching will also come with certain amount of energy. Those together, when approaching along the axis, they are going to be repelled off. Due to that repulsion, energy is going to be deferred. Energy of the orbitals which are present along the axis is going to be entirely different from that of the orbitals which are present in between the axis. That is it. You have to remember this much. When that is the case, in case of octahedral, I show you energy of dx square, y square, and dz square. Dx square, y square, and dz square which are present along the axis, they are completely repelled by the ligands. Energy is going to be increased. Dx square, y square which are present along the axis, they are going to show higher energy. Energy is increased because they are repelled. Okay. Similarly, the rest of the orbitals which are not present along with the axis, their energy is decreased relatively. Energy of dx square and dz square. What are the other orbitals which are present in between the axis? They are said to be dxy, yz, and dxz. dxy, dyz, dxz, which are not present along the axis. They are present in between the axis. Now what happens? This energy relatively is decreased. So this decreased energy with respect to orbitals which are present along the axis itself is referred as degeneracy lifting. Degeneracy lifting is nothing but certain orbitals will show higher energy, certain orbitals are showing relatively smaller energy with respect to these orbitals. So the reason why in case of octahedral, I have written all these points. In octahedral complexes, degeneracy is going to be altered when ligands approach along the axis. Orbitals which are present along the axis are completely going to be repelled by the ligands. Ligands are repelled and orbitals which are present along the axis are repelled. Energy is going to be increased. What are those orbitals present along the axis? They are dx square, dz square. You can see here. We have dx square, dz square. Here also we have dx square and dz square. In between the axis where they are approaching, there is no any repulsion is seen. In case of octahedral, these are the main orbitals are going to be repelled. So once they are repelled, we have to represent in a proper way. in a coordination compounds way. The crystal field theory have given a proper representation of all these degeneracy lifting. Fine, we will see that one by one neatly. Please do copy this one if you feel it is very necessary. Otherwise, no issue. Directly we consider the examples and we go on doing them. Fine. I hope you will be copying this one. Please do copy. We'll move to next. Welcome back, dear students. We'll see crystal field splitting diagram. How does a splitting degeneracy is going to be lifted in octahedral complexes? Nodri, first correct agi na ಏನು ಹೇಳತೀನಿ ಕೇಳಿಸ್ಕೊಳ್ಳಿ. Right? ಇಲ್ಲಿ ನೋಡಿ, these are said to be 5D orbitals, degenerate orbitals of a transition metal. ಯಾವಾಗ ಈ ತರ ರಿಪ್ರೆಸೆಂಟ್ ಮಾಡ್ತೀವಿ? ಇನ್ ಅಬ್ಸೆನ್ಸ್ ಆಫ್ ಲಿಗ್ಯಾಂಡ್ಸ್ ಅಪ್ರೋಚ್. ಲಿಗ್ಯಾಂಡ್ಸ್ ಇನ್ನೂ ಬಂದಿಲ್ಲ, ಅಪ್ರೋಚ್ ಆಗಿಲ್ಲ. ರೈಟ್? ಅವಾಗ ಇವೇನಿರ್ತಾವ, 5 ಹ್ಯಾಪಿ, ಆಲ್ ಆರ್ ಈಕ್ವಲ್. ಈಗ 5 ಜನ ಅಣ್ಣ ತಮ್ಮರೇನು ಇರ್ತಾರಲ್ಲ, ದೇ ಆರ್ ವೆರಿ ಹ್ಯಾಪಿ, ದೇ ವಿಲ್ ಬಿ ವೆರಿ ಕೂಲ್, ದೇ ವಿಲ್ ಬಿ ಡೂಯಿಂಗ್ ದೇರ್ ವರ್ಕ್ ಇನ್ ದ ಫೀಲ್ಡ್ ಅಂಡ್ ದೇ ವಿಲ್ ಬಿ ಪ್ರಿಪೇರಿಂಗ್ ಎವ್ರಿಥಿಂಗ್ ಆನ್ ದೇರ್ ಓನ್ ಅಂಡ್ ದೇ ವೇರ್ ವೆರಿ ಹ್ಯಾಪಿ. 5 ಜನರಿಗೆ ಮದುವೆ ಆಗ್ಬಿಡ್ತೈತ್ರಿ. 5 ಜನ ಅಣ್ಣ ತಮ್ಮರಿಗೆ ಏನಾಗ್ತೈತಿ? ಮದುವೆ ಆಗ್ತೈತಿ. ಮದುವೆ ಆದ ತಕ್ಷಣ ಏನಾಗ್ತೈತಿ? ಒಬ್ಬಾಕಿ ಹೆಂಡತಿ ಪೂರ್ತಿ ಅಂದ್ರೆ ಒಬ್ಬ ಅಣ್ಣಗೆ ಏನು ಮಾಡ್ತಾರ? ಪೂರ್ತಿ ಬಡವರ ಹೆಣ್ಮಗಳನ್ನ ತರ್ತಾರೆ. ಅದೇ ಥರ ಬೇರೆ 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 ಮನಿತನದಿಂದ ಬೇರೆ ಬೇರೆ ಹೆಣ್ಮಕ್ಳು ಬರ್ತಾರೆ. ನಿಮಗಂತೂ ಗೊತ್ತೈತಿ, ಎಲ್ಲರೂ ಸೇಮ್ ಇರಂಗಿಲ್ಲ. ಎಲ್ಲರದು ನೇಚರ್, ಎಲ್ಲರದು ಬಿಹೇವಿಯರ್ ಏನಿರ್ತೈತಿ? ಚೇಂಜ್ ಇರ್ತೈತಿ. ಅದರೊಳಗೆ ಇಬ್ರು, ಒಂದನೇ ಅಣ್ಣ, ಒಂದನೇ ಮಗ, ಎರಡನೇ ಮಗ ಏನಿರ್ತಾರಲ್ಲ, ಭಾಳ ದುಡಿತಿರ್ತಾರೆ. ಅವ್ರು ಭಾಳ ಸ್ಟ್ರಾಂಗ್ ಇರ್ತಾರೆ. ಆಮೇಲೆ ಅವ್ರಿಗೆ ಎಲ್ಲದ್ರ ಬಗ್ಗೆನೂ ಐಡಿಯಾ ಇರ್ತೈತಿ. ತಮ್ಮ ಮಗುಗಳನ್ನ ಚೆಂದಾಗ ನೋಡ್ಕೊಂಡು ಹೋಗ್ತಿರ್ತಾರೆ. ಒಂದನೇ ಅಣ್ಣಗೆ, ಎರಡನೇ ಅಣ್ಣಗೆ ಹೆಂಡತಿ ಬರ್ತಾರಲ್ಲ, ಅವಾಗ ಫೈಟಿಂಗ್ ಸ್ಟಾರ್ಟ್. ನೀ ಇಷ್ಟು ದುಡಿತಿ, ಇಷ್ಟೆಲ್ಲ ಮಾಡ್ತಿ, ನೀ ಅವ್ರಿಗೆ ಯಾಕೆ ಕೊಡ್ತೀವಿ? ನೀ ಇಷ್ಟೆಲ್ಲ ದುಡಿತಿ ಮಾಡ್ತಿ, ನಮ್ದು ನಾವು ಮಾಡ್ಕೊಳ್ಳೋಣ, ಅವ್ರಿಗೆ ಯಾಕೆ ಕೊಡ್ತೀವಿ? ಸ್ಟಾರ್ಟ್, ಫೈಟಿಂಗ್ ಸ್ಟಾರ್ಟ್ಸ್. ಸೆಪ್ರೇಟ್ ಆ್ಯಸ್ ಡೇಸ್ ಗೋಸ್, ಸ್ವಲ್ಪ ದಿನ ಹೋದ ನಂತರ ಏನಾಗ್ತೈತಿ? ಫ್ಯಾಮಿಲಿ ಈಸ್ ಗೋಯಿಂಗ್ ಟು ಬಿ ಸ್ಪ್ಲಿಟ್. ಇವ್ರೊಂದು ಕಡೆ ಹೋಗ್ತಾರೆ, ಅವ್ರೊಂದು ಕಡೆ ಹೋಗ್ತಾರೆ, ಅವ್ರೊಂದು ಕಡೆ ಹೋಗ್ತಾರೆ. ತಮ್ಮದೇ ತಾವು ಜವಾಬ್ದಾರಿ ಬೀಳ್ತೈತೆ, ತಾವು ಮಾಡ್ಕೊಂಡು ಹೋಗಕ್ಕೆ ಸ್ಟಾರ್ಟ್ ಮಾಡ್ತಾರೆ. ಸೇಮ್ ಕಾನ್ಸೆಪ್ಟ್, ಡೈಲಿ ಲೈಫ್ ಕಾನ್ಸೆಪ್ಟ್ ಯು ಕ್ಯಾನ್, ಆರ್ ಎಕ್ಸಾಂಪಲ್ ಯು ಕ್ಯಾನ್ ಅಪ್ಲೈ ಹಿಯರ್. ಇವು ಏನಿವ 5 ಆರ್ಬಿಟಲ್ಸ್, ಎದುರು ಮೆಟಲ್ ಅಯಾನ್. ಯಾವಾಗ ಈ ಥರ ಇರ್ತಾವೆ ಇವು ಹ್ಯಾಪಿಯಾಗಿ, ಲಿಗ್ಯಾಂಡ್ಸ್ ಯಾವಾಗ ಬರಂಗಿಲ್ಲ. ಲಿಗ್ಯಾಂಡ್ಸ್ ಅಂದ್ರೆ ಏನು? ಹೆಂಡತಿಗಳು. ಇವ್ರು ಬಂದ ಅಪ್ರೋಚ್ ಆದಾಗ ಏನಾಗ್ತೈತಿ? ಎನರ್ಜಿ ಆಫ್ ಆಲ್ ದೀಸ್ ಈಸ್ ಗೋಯಿಂಗ್ ಟು ಬಿ ಇನ್ಕ್ರೀಸ್ಡ್ ಸ್ಲೈಟ್ಲಿ. ವೆನ್ ಎನರ್ಜಿ ಇನ್ಕ್ರೀಸಸ್ ದೇ ವಿಲ್ ಬಿ ಮೂಡ್ ಅಪ್. ಎನರ್ಜಿ ಇನ್ಕ್ರೀಸ್ ಆಗೋದನ್ನ ಈ ಥರ ರಿಪ್ರೆಸೆಂಟ್ ಮಾಡ್ತೀವಿ. So once the ligands approach here, okay, orbitals with ligands approach. Ligands approach ಆದ ತಕ್ಷಣ ಏನಾಗ್ತೈತಿ? ಡೈರೆಕ್ಟ್ ಸ್ಪ್ಲಿಟ್ಟಿಂಗ್. 2 ಒಂದ್ ಕಡೆ ಹೋಗ್ತಾವು, 3 ಆರ್ಬಿಟಲ್ಸ್ ಒಂದ್ ಕಡೆ ಬರ್ತಾವು. 2 ಆರ್ಬಿಟಲ್ಸ್ ಮೇಲೆ ಹೋಗುವಂಥವು ಯಾವುವು? ವಿಚ್ ಆರ್ ಪ್ರೆಸೆಂಟ್ ಅಲಾಂಗ್ ದ ಆಕ್ಸಿಸ್. ಇಲ್ಲಿ 2 ಆರ್ಬಿಟಲ್ಸ್ ಅಲಾಂಗ್ ದ ಆಕ್ಸಿಸ್ ಯಾವ ಇದ್ವು? dx² y². I have written here. Right? Next ನೀವು ನೋಡಿ, ಕೆಳಗೆ ಬಂದಂಥವು ವಿತ್ ರೆಸ್ಪೆಕ್ಟ್ ಟು ದಿಸ್, ಕೆಳಗೆ ಆ್ಯಕ್ಚುಲಿ ಬರಂಗಿಲ್ಲ ಇವ. ವಿತ್ ರೆಸ್ಪೆಕ್ಟ್ ಟು ದಿಸ್ ಒನ್ ಐ ಹ್ಯಾವ್ ಶೋನ್ ಹಿಯರ್ ಬಿಟ್ ಬಿಲೋ. ನಾಟ್ ಐ ಹ್ಯಾವ್ ಶೋನ್, ಇಟ್ ಈಸ್ ಅಕಾರ್ಡಿಂಗ್ ಟು ಕ್ರಿಸ್ಟಲ್ ಫೀಲ್ಡ್ ಥಿಯರಿ. ಬಿಟ್ ರಿಲೇಟಿವ್ಲಿ ಆಫ್ dx² y² and dz², this energy is less. That is it. ಅದನ್ನು ಯಾವ ಥರ ರಿಪ್ರೆಸೆಂಟ್ ಮಾಡೀವಿ? t ಆರ್ಬಿಟಲ್ಸ್ ಆರ್ ರಿಟನ್ ಬಿಲೋ. ಎಕ್ಸಾಕ್ಟ್ಲಿ ಮಿಡಲ್ ಒಂದು ನೀವು ಲೈನ್ ಇಲ್ಲಿ ತೆಗೆದ್ರಂದ್ರೆ ಅದಕ್ಕೆ ನಂತರ ಬ್ಯಾರೀಸ್ ಸೆಂಟರ್. It is exactly middle line between the EG orbitals and T2G orbitals. Now question arises, what do you mean by EG and T2G? G stands for gyrate energy. Gyrate, ಅದನ್ನು represent ಮಾಡೋದು. EG orbitals are nothing but those orbitals which have moved upwards, and T2G orbitals which are those which have come downwards. What are those? ಕೆಳಗಡೆ ಬಂದಂಥವು ಯಾವುವು? dxy, yz, dxz. ಮೇಲ್ಗಡೆ ಹೋದಂಥ ಆರ್ಬಿಟಲ್ಸ್ ಯಾವುವು? ವಿಚ್ ಆರ್ ಪ್ರೆಸೆಂಟ್ ಅಲಾಂಗ್ ದ ಆಕ್ಸಿಸ್, dx² y² and dz². ಆ್ಯಂಡ್ ನೆನ್ಪಿಟ್ಕೋರಿ, ಈ ಡಯಾಗ್ರಾಮನ್ನು ಡೆಫಿನೆಟ್ಲಿ ಕೇಳಬಹುದು ನಿಮ್ಮ ಎಕ್ಸಾಮ್ಗೆ. ರೈಟ್? ಮಿಡಲ್ ಇರೋದು ಬ್ಯಾರೀಸ್ ಸೆಂಟರ್. ಇಲ್ಲಿ ನೋಡಿ, 2/5 delta O is the representation of energy. O represents that octahedral splitting, and delta, it is a value for EG orbitals, it is 3/5. ಹೆಂಗೆ ನೆನ್ಪಿಟ್ಕೋರಿ? ಇಲ್ಲಿ ನೋಡ್ರಿ, ಮೇಲ್ಗಡೆ 2 ಆರ್ಬಿಟಲ್ ಸ್ಪ್ಲಿಟ್ ಅಪ್ ಆಗ್ಯಾವ, ಅದ್ರದ್ದು ಅಪೋಸಿಟ್ 3/5. ಕೆಳಗಡೆ 3 ಆರ್ಬಿಟಲ್ ಸ್ಪ್ಲಿಟ್ ಅಪ್ ಆಗ್ಯಾವ, ಇದ್ರ ಅಪೋಸಿಟ್ 2/5. 5 ಅಂತೂ ಎರಡು ಕಡೆ ಕಾಮನ್. 3 ಇದ್ದಲ್ಲಿ 2 ಬರೀರಿ, 2 ಇದ್ದಲ್ಲಿ 3 ಬರೀರಿ. ಮುಂದ್ಗಡೆ ಡೆಲ್ಟಾ O ಅಂತ ಬರೀಬೇಕು. ದಿಸ್ ಮಚ್ representation of energy of these orbitals is needed. It is called as crystal field splitting diagram. Crystal field splitting diagram for octahedral complexes. For octahedral complexes. I hope this is 100% clear for you. Previous ಏನೇನು ಡಿಸ್ಕಸ್ ಮಾಡಿದ್ವಿ ಅದನ್ನು ಕೇಳಂಗಿಲ್ಲ. But in order to understand this splitting diagram, we need to have idea of the orbitals of central metal atom. So please do copy this. We'll move to tetrahedral complexes. Dear students, before I start with the tetrahedral complexes, I must tell you regarding the ligands. So for many discussion we have done in valence bond theory, but we couldn't get a clear picture or clear idea regarding strong field, weak field ligands. The clean and very well explanation can be given with the help of crystal field theory for weak field ligands as well as for strong field ligands. Just come here and see that arrangement of ligands according to increasing field strength. This is said to be a spectrochemical series with the help of various experimental data. They have given this arrangement of ligands. So here arrangement of ligands is done with increasing field strength. You can see here halogens I minus, Br minus, Cl minus, F minus, which is coming in the beginning of the series are said to be weak field ligands. I have given you many of the examples. Also we have done some of the examples also in which we have studied almost halogens are considered as weak field ligands. In between we have certain oxalate, OH minus, water, NCS, all are said to be very moderate. They can also considered as weak field itself, but with respect to these halogens and thiocyano groups, these are showing a field kind of field strength more. That is it. And at the end what we have seen here, that is carbonyl cyanide are said to be most prominent or dominant field strength ligands. They give us very highest splitting. So I must show here that strong field ligands we can consider with the help of this spectrochemical series. This series is clearly mentioned in your NCERT. From the there itself I have written here, with which we can identify which are strong field ligands, which are weak field ligands. These are strong field ligands I'll mention here. Then I have weak field ligands. Okay. Then next let me consider moderate, or they are also generally considered as weak field itself, right? So as I told you, Cn minus, cyano and cobalt are said to be strongest field ligands. So strong field ligands Cn minus and Co, right? Ever remember these points. These are going to help you throughout the chapter to gain around 3 to 6 marks from the spectrochemical series of these ligands itself. Okay. What are weak field ligands? I told you I minus, Br minus, thiocyano group, Cl minus, F minus, sulfide, all are said to be generally weak field ligands. So all the halogens will be considered as weak field ligands. Okay. Here moderate I have written EDTA, NH3 and NCS will be giving us a moderate kind of. Generally they can also be coming under strong field only. Whenever we write example for NH3 and EDTA, we can consider them as strong field itself, but not as strong as of Cn and Co. Okay. But while calculation we must have to use EDTA NH3 as EDTA NH3 En as strong field ligands itself. Okay. EDTA NH3 EDTA ammonia. Okay. then ethylene diamine. All are said to be set of strong field ligands. And all the halogens are going to be considered as weak field ligands. Okay. Then very strong, I told you these two are very strong. These are moderately strong, but while calculation we can consider them as strong field ligands itself. Now question arises, why does this classification is done? What exactly meaning of strong field? What is that field means? What is that kind of classification we have done on the basis of what? Field in the sense I told you, whenever ligands approach to the orbitals of the central metal atom, splitting of the energy causes. I have shown you diagram here with 2-3 orbitals. Here this field after splitting of orbitals which is obtained here itself is called as crystal field, and splitting is seen. Now question arises, strong field ligands when they are approaching, they will cause highest splitting field. When weak field ligands are approaching, there is no such of the gap between, very less, negligible amount of splitting field can be seen. For weak field ligands at least, there is no splitting at all, electrons will pair up there itself. When the field between two orbitals is highest, they are said to be strong field ligands. Due to approach of strong field ligands itself, splitting will be highest. Weak field ligands doesn't cause any splitting, almost they are same only. So this is all about the spectrochemical series. Just have a knowledge with this one. We'll move to the tetrahedral complexes. How does splitting will be seen in those? We can understand. Please do copy this. We'll move to next. Now let us understand crystal field splitting in case of tetrahedral complexes. Tetrahedral complexes, as name itself suggests, there are only 4 ligands will be approaching to the metal orbitals. And metal orbitals which are present in between the axes are going to be repelled by the approaching ligands. I have shown here a diagram. Do concentrate. This is the diagram of d orbitals. We have X, Y, Z here, right? Ligands are approaching in between the axes. What are the orbitals present in between the axes? You would have noticed with the previous session that dxy, dyz, dxz are said to be orbitals present in between the axes. So when ligands are approaching here, definitely the orbitals which are present in between the axes are completely repelled, and their energy is going to be increased compared to that of the orbitals which are present along the axis. That's it. Now do concentrate. I have represented here dxy, dyz and dxz, which are the orbitals present in between the axes, will have higher energy than the orbitals which are present along the axis dx square and dz square. Now as I shown you crystal field splitting in octahedral, we will see the same case in tetrahedral. This diagram representation is referred as crystal field splitting in case of tetrahedral complexes. In tetrahedral complexes. Now see what happens. As in case of that itself, we have orbitals before the ligands approach. Orbitals before ligands approach. They were very quiet, calm, happy, everything. When ligands are approaching, their energy is slightly increased. Ligands approach. Okay. When the ligands approach to the orbitals, some of the orbitals will have higher energy, some of them will have lower energy. Here, higher energy orbitals whose energy is increased are dxy, dyz and dxy, dyz, dx square, y square, it is not that, dxz, dx exit. Okay, so these are the 3 orbitals whose energy is increased, right? And it is represented as T2. Previously we used to mention as T2G and EG. Here we just represent as T2, and it is going to be represented as E. What are the orbitals present over here? Dx square, y square and dz square. Okay, and tetrahedral splitting value is represented as delta T. Here in case we have 3 orbitals, we will be writing as 2 by 5. Here we have delta T would be written as 3 by 5, right? And this is referred as delta T change in splitting, that is difference occurred in case of tetrahedral complexes is mentioned as delta T 2 by 5, delta T is 3 by 5. That's it. And one more point I have to mention here, the splitting energy will be highest for tetrahedral than that of octahedral. Why? Why? Because in case of octahedral complexes, there are 6 ligands are approaching and repulsion is very high. They show highest field of splitting than that of the tetrahedral. I must mention here that delta T tetrahedral splitting is less than that of delta O, that is octahedral. Octahedral complexes show highest splitting than that of the tetrahedral complexes. The difference of that value is delta T equal to 4 by 9, the greater than that of delta O. This value can be asked for your competitive examination. Apart from this, rest of the diagrams and explanation regarding these complexes can be asked for your board examination for 3 marks. So like this, we need to write each and every point with respect to tetrahedral splitting as well as with respect to octahedral splitting in complexes. So please do copy this. We'll move to the next. Now let us understand regarding coloring property in case of coordination complexes. When you consider coordination complexes like titanium H2O6, hexa aqua titanium chloride, if you consider this one, it will be generally shows a color for whole complexes. When you heat this complex, it will loses its color and it will become colorless. In the sense that I will explain further here. Colored compound is heated, it will be releasing its color. Then we have copper sulfate, hydrated copper sulfate. If you consider this one, it is having blue color. When you just heat it, it is going to lose the color and it will become white. Okay. And lastly, we have ruby here. You need to tell me what will be the color for this one. L2, ruby, a stone. It is considered to be a stone in which aluminum is transition metal present. So here, when you consider titanium, H2O, hexa aqua, H2O. How many are there? 6. Cl3. Can you say that it is octahedral complexes? There are 6 ligands are approaching. Titanium, we know that it is after scandium, titanium is going to, titanium is the next number. 3D2, 4s2 will be the configuration for titanium. 3D2, 4s2 is the configuration, right? I am explaining for this complex. Now, in this case, titanium is present with respect to +3 oxidation state. +3 oxidation state in the sense we left with only 1 electron in D. Now, let us consider octahedral complexes. When you consider octahedral, there are 6 ligands will be present. 3D, 1 is there. In the sense, we will have octahedral complexes splitting. We have seen T2G, EG. We will be considering 3 orbitals here and we will be considering 2 here. Only 1 is there. We have to represent that electron here. 1 electron is represented. When this electron moves to higher energy state due to absorption of certain amount of energy, it moved to T2 to EG. C. This is T2G. This is EG. Okay. Now it moves to EG. Electron just like this. 1, 2, 3. Right? When it absorbs certain amount of energy, it moves to higher energy state. It is unstable. This is higher energy state and it is said to be ground state. When this moves to ground state to higher energy state, it will be unstable here and it will be coming back to the ground state. While coming back to the ground state, it releases certain amount of energy. Initially, it is going to absorb energy, it moves to higher energy state. While coming back to ground state, it releases certain amount of energy. That energy is seen as color in a visible range. In a visible range. That is called as coloring property for these coordination complexes. What happens here? Initially, it is colored compound due to presence of ligands. When ligands are going to be heated or they are taken away, it is going to become colorless due to presence of ligands itself. Aqua is moderately filled ligand. It is neither strong nor weak, but moderately it causes certain splitting. So, due to presence of aqua, it has color initially. Once you heat it, water is going to be evaporated. In the absence of ligands, titanium transition metal will show colorless. It will be considered as colorless. Similarly, you can consider here, in case of water, in presence of water, copper sulfate shows blue color. When you just heat it, it will be releasing its color due to evaporation of water and it will become white. So this is all about the coloring property exhibited by certain coordination complexes we need to understand. Coloring property exhibited by coordination complexes is mainly because of ligands approaching to them. That's it. Do copy this. Next we'll move to metal carbonyls.